This is video 2 in our series, Analytical Mechanics. Before we get going here, a reminder that the playlist for all the videos is at the website, digital-university.org. What we're going to do in this video is exactly what we did in the first video. Hopefully you've had a chance to watch that. Only we're going to generalize it so that we're not dealing with an integral of just arc length, but of generalized functions, and obtain a more general expression. And remember now from calculus that if we have some curve here, we could find the maximum points, the minimum points, the inflection points by taking the first derivative and setting it equal to 0, then finding those values of x that make that 0. And right now we'll just say those identify stationary points. The stationary points could be maximum, minimum, or inflection. We would have to do other mathematical work beyond that to identify specifically what we have. In this video, we're just going to be concerned with identifying the stationary points of a particular kind of functions. So what we're going to do is look at, like I say, a more general case than what we had considered in the previous video, but the logic that's involved is exactly the same. We tried to explain all those steps in some detail in that first video, so we're going to use that as background. But here, what we have, we're going to work with is this type of general function. And to give an example as to what this might mean, suppose that we had a function that looked like this, and we're going to rotate it about the x-axis and then find the surface area of that revolution. And the general integral expression for that would be 2 pi y ds, integrating that from whatever these endpoints are. And then ds we could write like this, 1 plus y prime squared dx, or we could write it as 1 plus x prime squared dy. Of course, this is dy dx. So here, x is the independent variable. This would be dx dy. Y is the independent variable. So we could write out the integrals for the area of revolution either like this or like this. Of course, we would do it in this form because here we have y dy. But if we had an integral of this form, this would just be some function of y and y prime being dy dx. In this form, the one that we'd actually work with, that would be a function of y and x prime, where x, of course, is just dx dy. So here we're considering a more general case. X is the independent variable, so we have some function of x, y, and dy dx. And just as we did in the last video, we're considering small y of x to be the stationary function. That is, it'll either be the maximum or the minimum of this integral. And all the other ones, the ones designated with the capital Y's, are the ones that are not the maximum or the minimum, as the case may be. And the way we constructed the big Y's, we do it exactly as we did in the previous video. It's this. And again, we explain the logic behind this and what this arbitrary function nu of x looks like, how it's 0 at the endpoints x1 and x2. We covered that in the first video. So this integral, we'll just call it I, it is a function of epsilon. because y is a function of epsilon, and y prime, which is dy dx, that equals y prime of x plus epsilon nu prime of x. So both y and y prime depend upon epsilon. So our integral here is a function of the parameter epsilon. And what you saw us do in the previous video was to proceed to find the derivative of that integral with respect to epsilon, and we wanted it to be 0 when epsilon equals 0. Those were the two conditions, and that's what we're going to do exactly in this video, same thing. So here's our function, our generalized function. Now, to take the derivative of the integral with respect to epsilon, that means taking the derivative of this with respect to epsilon. Now here we could say, well, we have the partial of f with respect to x, then the partial of x with respect to epsilon. But that's going to be 0 because x does not depend upon epsilon. Only capital Y and capital Y prime depend on epsilon. So to take d epsilon of our integral, that would mean it's going to look like this. Just this general function x, so we're going to have the partial of f with respect to y, capital Y, then the partial of capital Y with respect to epsilon, plus the partial of f with respect to capital Y prime, the partial of capital Y prime with respect to epsilon. Dx. This is our integral. This is the derivative of the integral with respect to epsilon. And here, this is y. Take the derivative of that with respect to epsilon. Don't need this anymore. Dy d epsilon, that's just going to equal nu of x. The derivative of that with respect to epsilon, that's 0. Then we have this term, so we'll have this times the derivative of that. That's going to be d epsilon over d epsilon, which is 1, plus this times the derivative of that with respect to epsilon. Well, that's just 0. So here then, partial y with respect to epsilon, that's just nu of x. And what about this? The partial of y prime with respect to epsilon. Well, here's y prime. Take the derivative of that with respect to epsilon, and all we're going to get is nu prime of x. So I'm not writing these as partial derivatives, but of course the answer is going to be the same. So that means this is nu prime of x. So let's take this out and put this in, and take this out and put this in. So we're going to have nu of x in place of this. And here we're going to have nu prime of x in place of this. dx. So this is then this integral, the derivative of this integral here, this general expression, the derivative of that with respect to epsilon is this. And we want this to equal 0 when epsilon equals 0. So you want this to equal 0, and we want epsilon to be 0. Well, when epsilon is 0, big Y equals small y. So that means here we replace big Y with small y and big Y prime with small y prime. So this is the partial, put small y here and put small y prime in here. Okay, so we're saying then we want this integral here to equal 0. And let's write this as two integrals. We'll have dx here plus the integral, another integral sign here. So this is going to be, it's going to be written like this, dx here plus that second part of the integral, x1 to x2, and that was the partial of f with respect to y prime. Then we had nu prime of x dx. And the sum of those two integrals has to be 0. Now, let's look at this integral, because it looks like this integral might be set up where we could handle it by considering integrating by parts. So let's see if we see this is nu prime. Remember how it works when you're integrating by parts. You have the integral of u dv equals uv minus the integral of v du. So this is going to be dv. Then v is just going to be nu of x. So let's write it like that. dv is nu prime of x. Then v is just nu of x. Same thing as we did, exactly the same thing as we did in the previous video. Then that means that if this is dv, this, what's left over, of course, has to be u. So we have u equals the partial of f with respect to y prime. So du, we can just simply write that as d dx of this partial of f with respect to y prime dx. So this is u, du is just that differential there. And this integral that we have right here that we want to treat by parts, that's going to be u times v minus the integral of v du. So let's write this down here. We have this integral x1 to x2, the partial of f with respect to y prime nu prime of x dx will equal u times v. This is u and this is v, so we have the partial of f with respect to y prime times nu of x minus this integral. Oh, before we do, let's not be too hasty. This goes from x1 to x2. Minus the integral of v du. There's v and here's du. So let's write it all out. This integral. And we have nu of x. Then we have this. Let's see if we can squeeze it in. D dx of this partial of f with respect to y prime dx. That is the partial with respect to y prime. We can write that a little neater. Okay, now remember again from the first video when we introduced this arbitrary function nu of x, we said that nu of x was 0 at these endpoints. So here nu of x is 0 at these endpoints, so this first term is 0. So this integral right here ends up being this integral right here. So what we're going to have then is, let's go up just a few more steps. Remember we had this integral plus this one equals 0. Well, now what we're going to have is this integral minus this integral equals 0, because this integral we treated by integrating by parts, and this is what we got for it. This is what we ended up with. So we're going to take this out and in place have minus this integral. So let's do that right now, and once we do that we're very close to the end. And hopefully you've watched the first video and realized this is exactly analogous to what we did in the previous video, but again we're doing it with a more generalized case. So you have minus the integral x1 to x2 nu of x d dx partial of f with respect to y prime dx. Okay, this is just what we had written down here, only hopefully a little bit neater. So we're going to get rid of all this now. We don't need it any longer. And remember what we've been trying to do all along is with this integral, take the derivative of it with respect to epsilon, and it has to be 0 when epsilon is 0. And what that boils down to now is that this integral minus this integral has to be 0. It comes out to be that way now after we did all of our manipulations. But here we can go ahead and write all of this under a single integral sign again. Here we have nu dx, and here we nu of x dx. Here we have nu of x dx. So we can combine this under one integral sign. So we're going to have the integral from x1 to x2, and then we'll have this partial of f with respect to y. Then we're going to have minus d dx, this term. The partial of f with respect to y prime, nu of x dx. And that has to equal 0. Okay, and again, hopefully as you remember from video number 1, this is completely arbitrary. So that means that here we have this integral. No matter what function we put in here as a function of x, it always has to be 0. Not just for certain functions of x, any one we can think of, any arbitrary function we can think of, put it into here, it always has to be guaranteed to be 0. And of course, the only way that could happen is, the only way that we could get this integral to come out to be 0 for every single function of x that we could possibly think of to put inside the integral is what's inside the integral then has to be 0. Which means then that this right here has to be equal to 0. So that implies that the partial of f with respect to y minus d dx, the partial of f with respect to y prime, that always has to be 0. Or when you see it in books, usually it's multiplying both sides by minus 1. You usually see it in this form, d dx. The partial of f with respect to y prime minus the partial of f with respect to y equals 0. And that's Euler's equation. And right now it might seem rather confusing because we just kind of worked it out for a general expression. Again, in the first video we did it for a specific expression and we explained each individual step in more detail. But what it means is that if we have some type of function like this, an integral sign, and we want to find the stationary functions for that integral, what we're going to do is end up taking solving a differential equation to find out which of the functions that we can obtain that will be the stationary functions for this integral. And we'll have specific examples of this in the future videos, so that if it seems confusing right now, look at the first video, review that again, look at the specific steps, they're exactly what we did here, then look at this one again, and then also in future videos work out specific problems here where we have an integral of some form like this, and then we will determine its Euler equation and then see what we had to do to solve it. So join us for those videos and we'll continue along here and try and work out some more specific examples.